In this video, we'll take a brief look at power series. These are the series that we have previously seen when we had these series expansion for the exponential function and the trigonometric functions, the sine and cosine functions. So let me define now what I mean by a power series. So the definition is that a sequence of the form ak equals ck times x to the power k turned into an infinite series gives rise to a power series. What's called a power series of the following form. We'll just add these terms up to get ck times x to the power k, with k going from 0 to infinity or from 1 to infinity. The main point is that we have these powers of x, this auxiliary variable x, which has its powers appearing in the infinite series. Okay, so this is a power series. Now, in order to study its convergence, I mean, power series are all over calculus. You will see, or might have already seen it in your Math 1050 module. Now, to study its convergence, the convergence, we can apply the ratio test. Okay, so we simply have to take the limit of ak plus 1 in absolute value divided by ak in absolute value as k tends to infinity. Well, what does it mean for such a sequence now? Well, it means that we have to take the absolute value of ck plus 1 multiplied by the absolute value of x to the power k plus 1 divided by the absolute value of ck. Of course, we'll have to take the limit of this, the absolute value of ck divided by the absolute value of x to the kth power. Now, of course, we can simplify here with x to the power k. Let me just do that, and we are left with 1x in absolute value, which we can just bring forward to write that this is the limit of the absolute value of ck plus 1 divided by the absolute value of ck as k goes to infinity. And the ratio test was about this limit. It is convergent, our series is convergent, if this limit is strictly less than 1. That is what the ratio test claims. But what does this mean? Well, it means that for x, because in a power series like this, we assume that we have this sequence of coefficients, and we want to decide for what values of x, of this auxiliary variable, will the power series give rise to something sensible, something that is an actual convergent value. Well, it has to satisfy, x has to satisfy this inequality in order for the series to be convergent. Rearranging this means that it is convergent if the absolute value of x is less than this limit of Well, we have to rearrange this inequality to get the absolute value of ck divided by the absolute value of k plus 1, ck plus 1 as k goes to infinity. Okay, so this is what we have found applying the ratio test to a power series. Gives us that a power series is convergent for values of x which are less than this limit of the ratios of coefficients in absolute value. Okay, so we have a special name for this limit of ratios of coefficients. This limit is denoted by r, and it is called the radius of convergence. The reason being for having this name, radius of convergence, is that the sum ck times x to the power k, with k going from 0 to infinity, converges if for values of x that are between negative r and r. Okay, so it's a radius for x to go both into the positive or negative direction along the real line, to have a convergent series. Okay, now if the ratio test again can be of course still applied for the divergent version of these claims. So if this limit is greater than 1, then the ratio test claims that we will have a divergent series. So simply by the ratio test, we also have that this power series is diverges for values of x that are outside of this interval of negative r to r, so outside of the radius, or having a bigger value of absolute value of x than the radius of convergence, will give us a divergent power series. So then the power series does not converge to anything. Now, to give you an example, or rather two examples, I will consider the following power series. I would like you to consider this power series of x to the power k divided by k factorial, with k going from 0 to infinity. I want you to find the radius of convergence for this series. Pause the video, calculate the radius of convergence, and put it in the box below. Okay, I hope you have paused the video. Now this radius is defined here as the limit of the absolute value of ck divided by the absolute value of ck plus 1 as k goes to infinity. Now what is ck in this example? Is the coefficient multiplying x to the power k. Well, that ck in this example is just 1 divided by k factorial. And of course then ck plus 1 is 1 divided by k plus 1 factorial, and with k going to infinity. I left off the absolute value signs because these are all positive values. Now of course we can simplify with k factorial to gain this expression for our sequence, the limit of which we are interested in, and this sequence, it diverges to plus infinity. Okay, so this is a divergent sequence that we had to calculate. It diverges to plus infinity, which means that the radius of convergence is infinite. That translates into saying that this power series converges for all real numbers. Okay? So this is the consequence of having an infinite radius of convergence. Now, the other example I would like you to consider is simply the sum of powers of x with k starting from 0 to going to infinity. Okay, what is the radius of convergence for this series? Pause the video and input your answer in the box below. Okay, so for this series, now what we have is simply ck being equal to 1. So what we really have is just 1 divided by 1 is just a constant sequence 1, which will have the limit, of course, being equal to 1. What does it mean? It means that our power series converges for values of x that are less than 1 in absolute value, so between -1 to 1. If we pick x in that interval, we'll get a convergent power series, and the ratio test also tells us that diverges, that the series will diverge for x that is greater than 1 in absolute value, so for values of x which are greater than 1 or less than -1. And that is something we have already seen or looked at when we looked at geometric series. And just to give you some ideas, so the first example converges for all x, and actually if you remember, this is the power series that gives rise to the exponential function. So e to the x has this power series for all x, and the second one is of course a geometric sum. So if x is between -1 and 1, this is the power series is going to be equal to 1 over 1 minus x. Okay, I hope you got these right, and I'll see you in the next one.